associated with it, and when you're analyzing it, you want to take into account this fact, right? So this is something that you'll see throughout this course actually, about how to look at data in a randomized manner. Under these two main themes, we'll talk about three problems today. The first is the birthday paradox. How many of you have heard of this before? Okay, quite a few. Great. So what this problem talks about is, if I walk into a room with k people, how likely is it that two people will share the same birthday, right? When I first heard of this paradox, actually, I was very taken aback, and we'll see why in a bit. And we'll see some very nice results related to this paradox today. The second thing that we'll talk about is the coupon collector's problem. So how many of you have actually heard of this one? Okay, great. So two people in the class. So say there was a cereal box which was giving out some coupons in them, and I wanted to collect all these different coupons. Let's say they were randomly put into these boxes as well. So how many boxes do I have to buy before I actually have all the different coupons possible, right? So these two problems are a little different from each other, but we'll see how we can approach them and analyze to get expected values for both. In this theme, we will also talk about the central limit theorem. Well, I guess most of you must be familiar with some basic versions of this, but today we'll talk about this from the viewpoint of the Chernoff-Hefting bound, and about how concentrated measures tend to be, right? Or how distributions behave around their expected values. Okay, great. Before we get to all these interesting stuff, we will talk about some very basic concepts which will recur throughout the course and today's class. The first is IID data. Now, how many of you know what that means? Will somebody tell me what it stands for?
Identically and independently distributed. Identical independently distributed data.
Correct. So what this stands for is independent and identically distributed data. So say I have a data set X with some points, X1, X2 through Xn. Each of these Xi's are drawn from some distribution d theta. So this is some process parameterized by this parameter theta. So say if this was a Gaussian, then it would have two parameters, right? So, the mean and the variance. So what it means to be identically distributed is that all of these points are drawn from the exact same distribution, right? So simply put, say I am tossing a coin, right? I toss n coins, and each of these Xi's represent what I get as a result of these coin tosses. Then the values that these Xi's can take are heads or tails, right? Further, the probability with which it would take a head or a tail is also the same. So the distribution is the same for all of these different Xi's, right? The second thing that IID has is the independence. So what it means to be independent is that what value X1 takes, say, is independent of what Xn takes, or any of the Xi's take. So if I was tossing different coins and they're all unbiased and unrelated, so whether X1 takes a head or a tail is independent of, say, what X10 takes, right? So that's what it means to be IID. And you'll find this, yes?
So you mentioned that the probability of getting a heads is the same as the probability of getting a tails.
Yeah.
But suppose that you have twice the probability of getting a heads.
Yes, that's possible.
That would still be IID, correct?
Yeah,
because it's the same for every toss.
Yes, exactly. So the probabilities for the different outcomes do not have to be the same. It can be anything. So I don't know. Say you have a deck of cards, and want it to be spades as compared to anything else. So it's 1/4 and 3/4 for the others, right?
Yeah.
But it has to be the same across all the different variables.
Okay.
So the distribution is the same for every distinct variable. Yes?
Can we liken it to each one of your X's up there is a coin that's identical to the, like, so X1 is a nickel, X2 is another nickel, and then when you flip them, they have the same probability each
Right.
time and the same distribution.
Right, they have the same distribution. Yes.
Would it also be similar if I have a coin, I flip it 10 times?
Yes.
Each 10 flips is one experiment.
Right.
So each one is 10
Each flip
flips.
is a different, each xi, right?
Oh,
If you had 10, like a set of 10 flips is one xi.
yeah.
Yeah, you
It
can
would still be
like-
the same.
Yeah.
So let's say it's the probability of getting 10 heads in a row or something.
Yes,
Then
absolutely.
it would be, each one
Right.
of them would be its own experiment.
Yes, so what it means to be identically distributed is that the distribution for x1 should not be different from what x2 has for its distribution, right?
Okay.
So the probabilities do not have to be the same as in the head-tail case, but yeah, the distribution is the same as well, right? So this IID assumption is something that you find recurring again and again. It's something very basic that you make throughout, and you'll see that it's something that makes your analysis way simpler, right? That is one of the prime reasons why we actually do it. It gives us some very nice properties towards the end, right? Another point that I'll make out here is that the theme throughout the course will actually be how we integrate all these different small IID random observations to form some sort of a complex model out of it. So I'll borrow one of Jeff's cartoons out here that he tells every year to explain what this actually means. I'm not going to draw, he actually does a drawing, but I draw very pathetically and I don't want to torture all of you. So I'll just describe it. So say there was a giant elephant and there were 3-4 people standing at different angles and observing it. So somebody's looking at the trunk, say, and thinks it's a giant snake, right? Somebody's at one of the feet and thinks it's the trunk of a tree, right? And so on. So there are these are all different observations. So say there are thousands of such observations that we make, then we get close to combining all of them together to get back what the actual model was, to get the elephant, right? So you want to think of data in this way. So when you have a set of points and you actually fit a model to it, it's not that you're just finding the best model for it. The model probably already exists. It's a process from which you have drawn your data points, right? And what it means to actually get the perfect model or the best model is to be able to come close to what this actual process was, right? So if you fit a line to some data points, it's not because that's, you just got it out of the air. It's probably because your data points most likely came from that line and you're trying to get close to it. Okay? Was there a question? Okay, great. So now that we have this out of the way, we can talk about, we'll start with hash functions now. Yeah, okay. So again, now we again have a data set with endpoints, right? And each of these, okay, I'll index it a little differently. Say this is an n if it's not here. So this comes from some n. This is a set. So does this mean that my variables or my data points can only take these discrete and integral values? No, right? So what these 1 to n are just placeholders of some array. And each of them represent some distinct outcome that your variable can take. So this could have been the head or tail problem, right? So this would just be this array with a head or a tail. And each of your x's could take, say, head or tail. So I guess everybody who's been coding for a while, I mean, you'll know what this means, right? Whenever you are trying to get distinct values, you encode it in some way so that each distinct value is mapped to some number, because that makes life so much simpler, right? So this could be all the words in some dictionary, or it could be the distinct birthdays So I put this here because we will be talking about it very soon. So here, the distinct number of values was 2. This is going to be something that's a very large number. This is going to be 365, right? Now, what a hash function will do is that it will enable us to index into these arrays in some way, right? So let's formally define what a hash function means, and then I'll talk about some examples, and hopefully that will make things clearer. So, so this random is actually not a part of its actual name, but we use it here to distinguish it from locality-sensitive hashing, which is something that you'll cover in this course at some point. So a hash function, h, is a function from this family of functions. Let's denote it by uppercase h. And this h goes from some domain sigma k to n. Right? So this is the range of values that your variables can take, right? And this is some way to talk about your input, or some way to symbolize your input. So one way to do this is to think of it in terms of a string of k digits, 0 or 1. So it's a binary representation of your input in some way. So why do we call these random hash functions? It's because we choose these functions randomly. So there's a family of functions which are going from this specific domain to this specific domain. So every time you define a family of functions, they'll all be having the same range, and yeah, the two domains will be the same, right? And you'll be choosing these functions from them randomly. But once you've chosen a function, it is a function after all, so it's deterministic. So every time you put in the same input, it will give you the same output. Between different calls of a function, you do not get a different value, do you? Right? So say my function was actually, I'll put in the name of some person, right? Say I put in my own name. And what it does is, it returns my birthday. So say it's 1st June. So then every time I put in my name into this function, it's going to return this value, right? But if I put in somebody else's name, it's going to return their birthday, say. It's not going to vary between different calls if I put in the same name or the same person, but it will vary depending on when somebody's birthday is, right? So this is just one function, but I want to create a family of such functions, right? Because I want to be able to choose a function from this family randomly. So say this was my function HA, and I had some function HB, which took my name in and returned my father's birthday, say, right? Or it took my birthday and it added 10 days to it. And we do this in a cyclic way, so that 31st December maps to 10th January, right? So that is another hash function for this. So this is how we would create a family of different functions for this particular family, right? So they're all going from this, it's taking a name as an input, and it's giving you a birthday at the end of it. This is part clear, yeah? Okay, great. So then, one thing that we want to note out here is that the probability right? So if I have two different input values, x and y, the probability that they take the same value under this function HA is 1 over n, where n is the number of distinct outcomes or the distinct values that it can take, right? So let's talk about some, yeah.
Is it inferred that the function has to have an equal chance of, so it's not like a Gaussian distribution of its outputs, it has to have even chance of, going to its left bound as to right bound, the function's output?
Yeah, in a way, yes. But, so, There. Yes, technically.
So,
No.
I just want to make sure I understand it. So we have like HA, HB, up to ...
Mm-hmm.
H whatever.
Mm-hmm.
And then they're deterministic hash functions that map onto some spot on an array.
Mm-hmm.
But you have a set of hash functions and you're choosing the hash functions randomly.
Yes.
Okay.
Yes, so that's where the randomness comes into place. Once you've chosen the function, it's deterministic. So it will give you the same value every time you put in the same input.
So it's like I had an array of hash functions and then I
Yes.
assigned a random number generator to it or something. And it just trying to think of some like
Yeah.
why, I don't know. I
So-
guess you'll tell me why. This is important.
Yeah, so you can think of it as a family of functions, right? Which are doing similar jobs, but they're mapping to like a different value in this distinct array, right? And you want to be able to choose these functions randomly. Okay. So let's talk about some examples maybe. So you'll probably be using this for your first assignment. So the most common one is SHA-1, and it's common because it's inbuilt into a lot of common programming languages like Java or Python. And what it does is it takes some input, again sigma k, so it's a string of zeros and ones, and maps it to 0 1s in, I think, 160. Yes, 160, a string of 160 such digits, right? So this process is actually very complicated. So if you actually have the output, there is no way you can map it back to what the input was, right? So this is one of the reasons why it was really commonly used for cryptography. And so this will actually give you one function, right? So it's taking your input and it's mapping it to some obfuscated, it's using some obfuscated process and it's mapping it out to some value, right? But you want a family of such functions, not just one. So how will you generate, say, 20 different functions from this? Yes?
You just do it 20 different times, and then each time you do it once, that's one function, you do it twice, it's two functions.
Not really. You would actually like, so even though the process is not really known, but every time you put in the same input, it's actually going to give you the same output. So if I just do SHA-1 of some input, it's every time it's going to give me the same output, right? Because it's a function again. So you want to be able to control what it maps to by doing something else. So yeah.
Well, I guess that's where I was confused on my previous question. If you have a set of hash functions, they're all deterministic. They all map to different spots on an array.
Mhm.
How do you randomize the hash functions without using some deterministic sense of spitting something that spits out hash functions, I guess?
So you'll see how we do it right now. So this was sum in H, right? And now we want to make a family of functions so that we can randomly get a function out of it. So one way to do it is to concatenate a string to it. So I will do SHA-1. Right? So let's say A was some string that you randomly made up, right? And then you would concatenate it to your input, and you would get, and then you would put it into SHA-1, right? And you can create this string many times in random ways, right? Does that sort of make sense? How this is different from just doing it with the same input every time?
Well, it's not the same. I guess I was thinking you could do it once and take that output and map that as the input for another instance of SHA-1. And then your random function would just, but.
So you're doing it in a cycle,
So you're running SHA-1 on an output of SHA-1, basically.
oh, you do it, okay,
Like chaining.
That was just my idea, I don't know.
a chain. I don't know how that would actually work, actually. It might make things a little more complicated. But yes, yes.
So in this case, we're getting the randomness by doing some sort of like pre-processing on our inputs?
In some way.
but we're still using the same hash function? Or does that,
So if you change A, you'll get different hash functions, right?
so then our hash function becomes both the A and SHA-1?
Yes, so once you do this, it would map to say some value y. But now say you did SHA-1 of some string B, right?
I see what you're saying, okay.
Yeah, it would map to say some value y prime. So now you have say 20 different functions like this. Now you can randomly choose a function out of this family. And that would be what you would be using for the process. Did you have a question?
Yeah.
Yes.
So the sigma k in this case,
Uh-huh.
what is precisely? Because
So it's some input, it's some way of denoting your input. Right? So it's this again zeros and ones in k digits.
okay.
I think you had a question first, yeah.
I think what he was asking was that the function is the same, we're kind of changing the input, no?
You're not
So
changing
this-
the you're not changing
Because
the
we're concatenating to the original string, but we're still using SHA-1, right?
Yeah, but so you want to actually find out different values for your same input, right? So you say it was the birthday thing again, right? So I want to find out this. My input is also defined, right? It's coming from some domain. So if I concatenate to it, it's changing the input temporarily within this function. But overall, your function will actually look like this, the HA of x. So this is just HA of x. This is HB of x. Right? Yes.
So you said get different functions for the same input, right?
Yes.
So wouldn't that be achieved by concatenating a different string to the same original
Yes.
input string?
Yes, and
So it
that's
would
what we're
be-
doing, right? So this is your input,
Yeah.
and this is the string that you're attaching to it,
Oh, okay.
right?
Okay. So you're adding a to x and you're
Right.
adding b to okay.
So this is called the sort. Don't ask me why, but that's what it's called, and this is your input. So this is one of the most commonly used hash functions. If you wanted to create your own hash function, say, there are a couple of ways in which you can do that. There are many ways in which you can do that. I'll just go over a couple right now. One is multiplicative hashing. So here, HA of x is the floor of m times the fractional value of x times a. So this, say, this is the floor function. Right, so it rounds it off to the lower value. It's the floor function. And the frac of 7.5 is 0.5. So it's the fractional part of it. So by changing a, again, you can change what the hash function is. M is the range of the domain that you're mapping to, right? And a is some real number, right? And what you want to note here is that this hash function is such that your input has to be some number. So say it was the birthday problem and I was putting in names, then I have to have some way to map each of these names to some number, right? And by changing a now, by changing the real value that I'm attaching to this part, I can create a new family of functions for it, right? So there's another way in which you can create hash functions. That's called modular hashing. So here, HA of x is equal to x mod a. So this is a number theory concept, and does anybody know what this means?
Equivalent? Congruent.
No, it's not congruence. It's a little different from that. This is, it's used as congruence as well, but this symbol is also used to mean modulus function. So if I was doing 12 mod 10, this would be 2. So it's like the remainder in some sense. So if I was doing 12 mod 20, this would be 12. Right? So this is one way of creating hash functions, but this is not recommended at all. So if you're actually creating your own hash functions for the upcoming assignment, this is not recommended. This is because there is some sort of bias out here, because if there are two numbers that are close to each other, say 12 and 13, and I was taking the modulus with 10, or there is no way that they would actually be mapped to the same value, right? And there are a range of different problems where this could go really, really, really wrong. So you would definitely not want to use this. So if you were actually creating, yes.
But like, isn't the point of hashing to get distinct values for different values?
It is, but okay. So the way to think about this is that for a lot of different processes, you actually don't want it to be so deterministic. Like when you're doing a modulus function, you're just mapping it to some remainder value. You're not actually going into a lot of details about what this represents,
Okay.
right?
So there's no way to like cluster values together or like group them together.
You could think of it that way, maybe. Oh, okay. Yes.
So should a hashing function be chaotic in a sense, where like small variations in your input can result in very large changes in what your hash value is?
That's one way to think about it, maybe. But you don't really want it to be chaotic, but you don't want it to be too biased as well.
To maintain like the thing that you said earlier, where the probability of the hash of two values being the same is like 1 for n.
Right.
Okay.
Yeah. If all of these probabilities are, you first, yes.
You want like as few collisions as possible in like a good hash function?
No, that's not the aim, I would say, of hashing. Yeah. So if you're actually creating your own hash function for this assignment, multiplicative hashing is one way to go about it, and it's easy to implement. You could also use a different, like many different kinds of hash functions, but they are generally more complicated. So I would recommend multiplicative hashing. So now that you've actually got hash functions, you have this array now, right, of different values. And these are all your n distinct values. And you have some hash function h. And every time you put in some input, it's taking it to some value out here, right? And you put in, say, h of p, it takes it to some other value, maybe to the same cell, maybe to a different cell, but it's taking you some place on this array. So now you can ask some interesting questions once you have this. So you want to know that if I keep doing this, if I keep giving inputs to my hash function, I've chosen this hash function now, and I'm giving it different inputs, how many times do I have to do this before I have a collision, right? That's what we're going to answer using the birthday paradox. The second question that we can ask is, how many times do I have to actually call this function with different inputs before I cover all the different cells? So how many times before each of these cells have at least one entry each, right? So that's the second kind of question that you can ask, and we'll answer that by analyzing the coupon collectors problem. So let's begin by just talking about the birthday paradox. I think things will, like hash functions and everything, will become a little bit clearer now. So let's start with the birthday paradox. So now this array is actually 1 through 365. I'm ignoring leap years. So this is January 1st all the way up to December 31st, right? And I want to know how many times, how many people do I have to ask, right? I'll ask them their birthdays, and how many such people do I have to ask before I have two people sharing the same birthday, right? Before I have a collision. So, so it's seen that if there are 23 people in a room, right? The probability that they share a birthday, or the probability of a collision, is about 50%. So this seems a little counterintuitive, right, when you first look at it? At least I found it to be counterintuitive when I first read about it. So there are 365 different possible values. And with just 23 people, you have a 50-50% chance that two people will share the same birthday, right? We will analyze this in a little bit, and we'll see that it indeed is true. Before that, we'll do a small simulation in class. So I'll ask different birthdays, all your birthdays in some random order, and just shout out the day and the month. And if we're on the right side of probability, we will actually see a nice result. Right? So let's start. I'll start from here.
January 21st.
Okay.
June 1st?
January 23rd.
30th June.
February that.
Um,
February.
11th. Okay.
June 6th.
Lots of Junes and Januaries.
July 4th.
Oh.
July 19th.
Okay.
November 5th. July 15th.
December 21st.
May 26th?
June 3rd.
January 8th.
Okay. Yeah. Yeah.
21st of August.
Yeah.
July 15th.
Oh. Okay. So we have a collision already. So how many people did it take us? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Not bad.
Almost, yeah.
So with 23 people, we had a chance of about 50%,
Yeah.
and we got a collision in about 15 people. Not too far off, right? So what you'll see is that there's actually a high variance distribution. Even though the expected value is somewhere closer to 23, you can find collisions in much larger values or much smaller values as well. Right? And so I'm guessing none of you in this room, you're twins or triplets or anything, so this is a very good distribution to actually, good random sample to actually do this on, right? So if I were to plot this, and my x-axis was the number of people I asked their birthdays, right? And this is the probability of a collision. Then this curve looks something like this. So let's see if this is 0.5. This is 23. This is about 50. And with 50 people, you go to a probability of 0.965. So if there are 50 people in a room, with 96.5% of the times, you'll see that you have two people sharing the same birthday. About 3.5% of the time, there won't be any collision, right? So this does seem a little counterintuitive, right? Yeah. So the range is actually somewhat like this. So if I had 18 people, this would be about 0.33. And with 28 people, it would be about 0.66. So a third of the time, between 18 and 28 people, I will have a collision. I'll have two people sharing the same birthday. And a third of the time, I'll need lesser than that. So today was one of those instances where we stopped before we even reached 18. And a third of the time, it'll actually take more than 28 people, right? So let's analyze this mathematically and see if we actually are, we expect some values like this. Right. So say I had two people in a room. Then what are the chances that they share the same birthday? Right. So let's do this generally. Let's call it just 1 by n, right? Then what is the probability that there is no collision, that they do not share a birthday? Seems fair, right? So now, with k people, there will be k choose 2 such pairs, right, that you can make. Then, the probability that you still have no collision, is it still legible? Not so much. So, k choose 2 is what? K times k minus 1 by 2, right? So I'm approximating it by k squared by 2. Then the probability that I don't have a collision now with k choose 2 pairs is this, right? 1 minus 1 by n to the power k squared by 2. So if I were to plug in values, if n was 365, k was 23, then this actually comes out to be 0.997 to the power 253, and this value is like 0.467. You can calculate it, you'll see it's something similar. That means
For k equals to?
for k equal to 23. Sorry, thank you. Right? So I was plugging in what we started off this problem with. So I have 23 people in a room. What's the chance that they actually share a birthday? 2 people share a birthday, right? So then, the probability of a collision is just 1 minus this, which is about 0.53, right? So it's like 53% chances that 2 people will share a room, share a birthday if there are 23 people in a room, right? So let's look at some more interesting properties. So what if k was square root of 2n? Then the k squared by 2 becomes just n, right? So this probability of having no collision is just 1 minus 1 by n to the power n. And most of you might know that this is just e power minus 1. So this is about 0.37. So with about square root of 2n number of people in the room, I will go to the interesting part of the curve. So I'm already somewhere here. So 37, right? So I'm somewhere here on the curve. So if there were n distinct possible values, and I have just square root n, calls to my hash function, then the probability of having a collision is already pretty high. So how is this important? Say there was a company which was sending out customer reviews, and it has 10,000 customers. and it sends out 10 or just 100 reviews, right? So 100 reviews, that's a small number, but it's doing it randomly. So there is a very high possibility that it sends 2 customer reviews to the same person, which means that this person is going to get annoyed and probably unsubscribe, and you don't want that. So this company actually needs to have a better plan now, right? So this is how you can see the effect of randomized algorithms or randomized data, right? Before we move on to the coupon collectors problem, let's see if where this actually breaks down, and it actually does break down. So can anybody spot how we can actually prove that this is not actually always correct?
Because you have a leap year.
I've taken n, right? So I can just change it to 366 and it'll still work well, right? Yes.
I think we assumed that people's birthdays are even distributed.
Yes, that's actually a very fair point. So it's seen that people have, there are more birthdays in spring as compared to winter. But also there are like twins and triplets and so on. But the effect that these will have on this is pretty negligible. So there's a bigger problem out here. Yes?
Multiple collisions, right?
Mm,
In the same room, in the same data set.
yes, but again, that's sort of covered here already. You just care about one collision, right? Yes,
When k greater than 365.
exactly. So when k is greater than 365, what does this look like? This value with k greater than 365 is still going to be some value that's greater than 0, right? But that's not true. If I had 366 people in this room and I was asking all their birthdays and I'm considering a non-leap year, then at least 2 people must share a birthday, right? So the probability of collision should be 1. But that's not the case when I actually use this formula. Right?
So you're talking about the pigeonhole principle? Like if you have 366, at
Yeah,
least one has to share a birthday?
yes, right.
Okay.
But you will see that this formula actually does not render that. So if you have,
Oh, okay.
because this value actually keeps getting smaller, but it's still a number greater than 0. Whereas if you were actually looking at 366 people and you were asking their birthdays, then the probability of having no collision should be exactly 0. Not some value close to 0, but exactly 0, right? So it is breaking down when k is greater than 365, or k is greater than n, right? So where did we go wrong? So instead of looking at different pairs, we want to actually look at the different possible outcomes. So if I had 2 people, then the chance that they actually do not share a birthday, or the probability of having no collisions, is n minus 1 by n, right? So if I had 3 people, right?
Why is it n minus 1 over n?
N minus 1 over n is just 1 minus 1 by n, right?
Oh,
We
okay,
already did that.
sorry, where n is the number of days.
Yes. N is the number of distinct possible outcomes. So now, if I have k people, this should just be n minus 2 over n, whereas we're now the second person. So the first person could have had a birthday in any of the other 364 days in the year, and there would be no collision, right? So the first person can have a birthday any day of the year, and there's no collision. But the second person has to have a birthday on 364 other days, and still there'll be no collision. When you have the third person now, he can now have a birthday on 363 days, so n minus 2 days, and there would be no collision. And so on. So now I have 4 people, all the way up to n minus k minus 1 over n. And this is what your probability of no collision should look like. Right? And you'll see when k is actually greater than n, or k hits n, this will actually go to 0 when k is greater than n. But this is actually a little harder to think about as compared to our first formulation. And you can't really see all of the different relationships that we were talking about a little while ago. which is why that is also acceptable. And if k is actually not as high as n, or like it's not greater than n, you can use either of the two formulations and have a very good approximate result. Right? Okay, so I think now we are ready to move on to the next problem. We have covered a lot of time. Okay, so I'll try to go over this a little faster. So this problem is a little different. In the previous problem, we wanted to have a collision, right? We wanted to know when two people would share a birthday. Now I want to know how many people do I have to ask before I have at least one person per possible birthday, right? So we saw that in the previous case, if we had about square root n, we had a high possibility that two people would share a birthday. Clearly, this is not the case here, because if you want to have one birthday at least, like you want to cover all the possible values, you need to have at least 365 people, right? Otherwise, you would not have covered all the different possible values. So it's going to be greater than equal to n, right? Your expected number of people. Okay, so since clearly there are not 365 people in this room, and also it would probably take forever if you wanted to do that, let's break it down and make it a smaller problem. Now I want to cover all the different months, right? So how many people do I have to ask before I have at least one birthday per month? So let's do another quick simulation. Before we start, any guesses to how many people do you think we'll need to ask here? Just a random guess.
20.
Let's talk in terms of n, like in random. So if there are n different distinct values, how many people do you think we'll have to ask? N cubed, n to the power n, exponential of n?
12 times n.
12 times n? So that's 12, that's n squared, right? Or in this case, or you're saying for any n it's just 12 times n?
No,
I would say
just
n
guess
times
it.
n squared.
N squared? Okay.
Worst case. Just throwing that caveat on there. So.
You can't really call that the worst case because it's a random sample. It could actually go much
Okay.
higher than that, right? These are all high
Yeah,
variance.
it's true. Yeah.
Yeah. Yes. 3n. It's not too far off, but there's a logic behind it. Yeah.
Maybe some kind of log.
Actually,
In log n.
that's actually pretty close. So it's n times natural log of n. Actually, there's another factor. It's log n plus some factor. You'll come to it, but that's what it looks like. So there's an extra log n number of people that you'll actually have to ask to come close to the expected number of value, expected number of people. So this is actually somewhere close to 36 or 37, I think. So it's in the high 30s. So let's see how many it takes today. Okay, let's start.
October.
Okay.
February.
September.
January 1st.
Oh, just tell me the month. No. Yeah.
June.
January.
You already have a question.
I'm not looking for a collision anymore, right? I'm trying to. So my problem now is that I want one entry in every possible cell. So I want to have one birthday per month at least, right? So yeah.
May.
May,
May.
February, July,
December?
September,
So what are the months that are left? August, November, and March. Okay.
February.
September.
Okay.
November.
Great. Yes.
March.
So August. Maybe.
December?
Okay. Mm-hmm.
May.
Nobody in August, huh?
May.
What? Don't tell me. I don't want to be biased. Okay.
October.
Okay. You almost said August there. June. Okay.
Yeah.
July.
December,
Okay.
January. January.
Okay. Who did I cover? Back there, yeah.
January,
I think I'm going to finish this class.
May, July,
Okay.
August.
Yes! So these are high variance events. It could have been that we would not actually have covered all the months, but I'm glad that we did. So how many did we take? 3, 4.
Exactly 37.
Is it?
Dun, dun, dun.
That's kind of spooky.
That's pretty close to 30.
It's 36, right?
That's not as spooky.
Is it? Did all of you get 37?
Exactly 3 ends.
So okay, it's yeah. So I may have counted. I think by the way I've counted it's like 36, but yeah. So we are really close to the expected value. I'm so happy, but that has nothing to do with what it should have been or anything. But yeah. So let's actually mathematically analyze and get this value, right? Yes?
Quick question. So here, what a probability do you, like the n times natural log of all that, that guarantees a probability of what?
So this is the expected number of people, or the expected number of coupons that I have to see before I see all the different coupons. So in this case, the expected number of people I have to ask before I have at least one birthday per month. Or at least one birthday in each month.
Is there a probability attached to that though? Or no?
So you'll see in the way we analyze it, there's of course a probability of having a birthday in a random month, right? It's 1/12 if we take it to be. Because birthdays are almost equally distributed across 12 months, right?
Yeah.
Yes, it is.
So I'm just curious, from probability and statistics, if the expected value for this would be like 12, if it was like dice rolls, for instance. So I'm curious, is the n log n the expected value formula specifically for the coupon collector's problem, or is it a general formula?
It's a general, so if you, what you're saying in this is that, yes, so if there are n different values that my variable can take, right? And, or n different values that a function can take, and I'm calling this function randomly several times. How many times am I expected to call this before I get all the different values possible? Right? So, more generally, like I motivated it, like I guess in the beginning. So if there were coupons in some cereal box, or McDonald's has these toy things, right? So there were 5 toys, and how many Happy Meals do I have to buy before I get all the different 5 toys, right?
Okay.
So that's one way of thinking about it. What is the expected number of times? The actual number of times I have to buy can vary, but what is the expected number of times that I'll have to buy it before I get all the 5 different toys, right? So how do we analyze this problem mathematically? This is a little more difficult to think about compared to the previous problem, but half the problem in a mathematical analysis is solved by just cleverly choosing variables. So what we'll do is, we'll define these variables Ri and Ti. Okay, we'll come to that later. So let's define Ri to be the number of random trials before I I see the I is confusing. Before, I'll just convert that to seeing I distinct coupons. Right? And let's define TI to be the number of trials between seeing the ith and I minus 1th distinct coupons. So if it took me 15 trials to see the 3rd distinct coupon and 25 to see the 4th one, so then my TI is just 10, right? So this is Ri minus Ri minus 1, right? So I want to find out what is the expected number of, okay, before we come to that, so what is the total number of trials that we see to see n distinct coupons? That's nothing but Rn, right? So Rn is the number of trials before seeing n distinct coupons, right? So this is nothing but the summation over Ti, right? Is that clear? Okay, so let's call this some variable t. Then I want to find out what is the expected value for R of n. So that is nothing but the expected value of t. So by linearity of expectation, we know that we can actually distribute this expectation over each of these ti's. So this is just expectation of t of 1 plus expectation of t of 2. This is 1, and so on. So this is expectation over summation of ti. Or sorry, the summation over the expectation of ti. Right? So if we can find out what these values are, we are done. So let's call Pi the probability of seeing the ith distinct coupon in some trial. Right? So I've already seen I minus 1 coupons. What is the probability that in the next run trial I see the ith distinct coupon? So that is nothing but n minus I minus 1 over n, right? Then you can see that this looks like a geometric distribution of sorts. So then expectation of Ti is nothing but 1 over Pi. So that is n over n minus I plus 1, right? I don't want to go to the next page, so I'll just make one here. So what this means is expectation of Rn is, and I lost it. I just need one small, yeah, sorry. Can you move it on to me? Thank you so much. I really don't work with the surface too much, so really sorry about this. Yes, great. So then expectation. Am I legible still? If I'm not legible, please let me know, and I'll write better.
And we're assuming the IID, that's why E, the expected value of TI equals 1 over PI.
IID, and also it sort of looks like a geometric distribution.
Oh, it's a geo,
Yeah.
That's where it is.
Yeah, that's why you can actually make that assumption.
Oh, okay.
But, so this expectation of Rn then becomes the sum over n minus I plus 1, right? Again, so this is a little harder to think about. Well, actually, actually no, but okay. So when I is 1, what does this look like? This is just 1 over n, right? When I is 2, this is 1 over n minus 1, and so on. When I is n, this is just 1, right? So this just looks like the sum over I, right? So you're just changing the way you look at this, this value. Now this may seem insignificant, but this is actually a very well understood number. So this is just the nth harmonic number, which is gamma times natural log of n plus some function of 1 over n. Now this is a very smaller order term. It doesn't affect your bigger problem too much, so we can generalize it to be just n times gamma plus natural log of n, right? So gamma is actually about 0.5. So if you were to actually plug in values of n and gamma, you would see that this expected number of people that you want to see is about 37. Right? Yes.
So is that constant the same for all colors of this nature? Is it always
Yes.
0.5?
Yes, this gamma is just a constant. That because you've brought it down to some harmonic number and it just comes from there. Right? Yeah.
How did you get the PI again?
The PI is the probability of seeing the ith distinct coupon. So you already have seen I minus 1 coupon so far, right? And now in the next trial, what is the probability that you see a new coupon? So it's n minus I minus 1 because you've already seen I minus 1 coupons over all the different distinct values.
And n is the number of trials?
N is the number of distinct values.
Okay.
Right?
You guys need to see all coupons?
Pn is yes.
No. Oh,
P.
yeah.
Yes. So this is Pn would be seeing the n distinct coupon, given that you've already seen n minus 1 coupons. Right?
Yeah, I'm sorry, I still seem to understand why it would be n minus I minus. Like, why is...
So there are n distinct values that your coupons can have, and you've already seen I minus 1.
Okay.
So now when in the next random trial, you want to know what is the probability that I see a new coupon, right? So you're discounting all the coupons that you've already seen, and now you want to.
And why is it the same as P of R though?
I'm sorry.
So it's the same as PR.
PR. Oh, PR is just probability. PR stands for probability.
Like, I thought it was...
There's no notation there. Okay. So yes, that is how we derive what we had started off with at the beginning of this problem. Now, so are we erasing this?
One question.
Yes.
Yeah. Could you explain that thing that we assumed to be summation 1 over I? That's it.
Yes. So this quantity out here, right? So if I was, you understand why I took n out, right? Because n is independent of I. Yeah. So if I put in I, so I'm varying I, right? So when I is 1, so it's 1 over n. When I is 2, it's 1 over n minus 1. And you go on. When I is n, it's just 1, right? So it's this. So this just looks like 1 over I, right? Right? So I've just changed the way we are looking at it. Okay. So
Wouldn't
what?
you index from 2 though?
What?
If you change that, would you index from 2?
No,
No?
no.
I have to look at it
Erased
closer.
it, but
Yeah, I believe you. I believe you. I mean, I believe you that the expected value is 1 over pi. So I might as well just believe you on everything else.
yeah, I think I'm running short of time, so
It's just.
I'll just move on a bit quicker. Yeah. Okay. Actually, it's fine. I think I'll go over it. So what happened was I was doing this right. Right? So when I is 1,
Right.
so it's 1 over n minus 1. It's 1 over n, sorry, right? When
Yeah.
I is 2, it's 1 over n minus 1. When I is n, it's 1 over 1, which is 1, right? So this is summation over 1 over I, right? 1 over 1 is 1. If you start your indexing from 2, this doesn't come into your summation, right?
I was looking at it different, like you counted the first term.
But this makes sense now?
That makes sense, yeah.
Great.
It's just some algebraic gymnastics.
Yes, exactly.
I got you.
Okay. So what if your probabilities were different now, right? So what happens, again, McDonald's problem. So there are 5 different toys, and if I get all 5 of them, I get some prize. So then one of them will be really hard to get, right? So say there are n different outcomes, each with probability pi. So p1, p2, all the way up to pn, right? And summation of pi's is 1. And let's call p star to be the minimum of pi, right? Then what you'll see is this comes out to look like something like the expected number of, roughly depends on this. It will come to actually depend on the lowest frequency. Yes.
Just some clarification. Is the probability for each chance the same or no?
In this case, it's not. Before,
Okay.
when we're doing we were doing with all the probabilities the same, right? So this is
Right.
one way in which we're breaking down the previous problem now.
So it's like if there was a golden ticket.
Yeah, exactly. So before it was like all the coupons were like, they were IID. They were all randomly distributed and identically distributed. All of them had the same probabilities of being there in your box, right? But now, some of them are more probable than the others, right?
Why?
Yeah. like-
Because, so,
Think
if you
like,
get all the
McDonald's.
coupons, you get a prize.
Well, they had the boardwalk game. There's only 2 boardwalk coupons.
Exactly.
If you win it, you get $1 million. And
Right.
Okay.
there's n coupons. You have like 2 over n probability. But to get something crappy like Baltic Avenue, it was like almost every other comp.
Exactly.
Right.
So if you get
Okay.
that one coupon, which is really rare, then you actually get your prize. So in real life, you'll actually have 1 or 2 coupons, which will be really, really, really rare. And this will get dominated by that probability, right?
So that would be the P star probability.
Yes, which is the minimum of all the different probabilities. So in our previous case, all of them had similar probabilities. They were IID. Now we're breaking it down. We're saying they're not IID. 1 of them or 2 of them are really rare. What controls this now, right? So now the expected number of trials that you'll need before you have all the different coupons is dominated by this P star, right? I don't think I can cover the central limit theorem today. I think that's fine. Professor Phillips will probably do it next class. What I'll do instead is I'll talk about a different case now. So what if I was now looking at a continuous interval instead of discrete values, right? So now I have, it actually looks a little similar. Yeah, so the probability of hitting one particular value in a continuous distribution is, I hear some 1s and some 0s. Who said 1? Okay, and who thinks it's 0?
Are you thinking of it as a point?
It actually is 0, because
Yeah.
in a continuous distribution,
Oh, yeah.
you can have, so there are infinite number of values, right? So hitting one particular value is actually 0. But now you can actually divide into intervals, right? And then you can define the probability that you hit an interval, right? So let's call that probability some epsilon. Yes,
So essentially you just discretize it and then it's the same.
yeah, in a way. So this will actually look like something like 1 over epsilon, log 1 over epsilon, where epsilon belongs in 0 to 1. There's a derivation for this, I think, in the notes for this class. But the point that I want to stress on here is that the expected number of values is actually greater than n, but it's a little less than n squared, right? So it's somewhere in between, yes.
Sorry, what does epsilon represent here?
So it's the probability that you hit one interval in this continuous distribution.
Is epsilon the interval?
But epsilon is the probability
Probability.
that you hit that interval. So you have some interval, and the probability that you hit it is epsilon. So you have some sort of a log factor associated with it, and so you need more than n turns with the higher probability, but you also need less than maybe n square trials, right? But again, these are all high variance events, and you might actually go up to a really large number before you see one birthday per different month of the year, or before you get all the different coupons. But there is a contrast that I can make out here. So in the birthday paradox, the mean was about 23, right? But the probability that there's no collision when we ask 50 different people is actually higher as compared to this case, where if we ask 50 different people, we'll probably have, we'll cover all the different months, right? So the variance in this distribution is actually smaller as compared to the birthday paradox, right? So the birthday paradox looked something like this. So this is actually kind of spread out. You can have something which has lower variance. Your graph could look something like this. So it's 0 for a while, and it hits some value where it has really high probability. It shoots up, and then it's almost the same, right? So that is what it means to have a very low variance, but both of these cases have a higher variance, but a coupon collector's problem has lower variance as compared to the birthday paradox. I think I'll stop here. I had planned to do the central limit theorem as we had discussed in the outlines. We did not get to it, but that will actually explain how close you get to expectation, and how to think about this concentration towards the expectation.